Hey there, and welcome to Mr. Lehan Teaches You Stuff. This is Grade 9 Chemistry Lesson 8, Bohr Diagrams. So if you're looking to make a Bohr diagram of an element, the first thing you need to do is draw a circle. And this circle represents the nucleus. In that circle, you're going to write the number of protons and neutrons that that element has. So let's choose an element. We're going to take sulfur. So here's the box for sulfur. And up at the top left, it says it has an atomic number of 16, which means it has 16 protons. So we'll write 16p in our circle. Next we need to figure out the neutrons. So we'll take our big number, subtract our little number. We get 32 minus 16 is 16 neutrons. So we put 16n. So the next thing we need to do is add the electrons. Now you need to remember that the number of electrons is equal to the number of protons. So since sulfur has 16 protons, we're going to have to draw in 16 electrons. And we put them in orbits or shells, and the first three shells can hold 2, 8, and 8 electrons. And each shell must be filled before another shell can be started. So we need to start with the first 2 in the first shell and then add 8 in the next shell, etc. And one last point, when we add electrons we have to pair them up after half filling the shell. So let's get started. The first one can hold 2 and we pair them up because it's more than half full. So we've got 2 electrons out of the way. The next shell can hold 8. So we put 8 in the second orbit there. And notice that they're all paired up because it's more than half full. And then the third orbit, we're already at, what is that, 10 electrons? We need 6 more to make 16. So we add 6 more electrons to that third orbit, or that third shell, and 2 of which are paired up, and then we have 4 I guess are paired up, and then 2 sort of lonely unpaired electrons over there. So that's it. That's the Bohr diagram for sulfur. So let's try a couple more. So now let's do a Bohr diagram of lithium. So first we draw the nucleus and figure out how many protons and neutrons lithium has. So lithium's got an atomic number of 3, so we know it has 3 protons. We can write that in. And next we need to figure out how many neutrons it has. It has an atomic mass, which is protons plus neutrons, of 6.94. So we round that up to 7. So it has 7 minus 3 neutrons, which is 4. So, long story short, take the big number, subtract the small number, you get the number of neutrons, 4. So next up is the electrons. And how many electrons is it going to have? It's going to have the exact same number of electrons as protons, so it's going to have 3 electrons. So first we add up the first shell, and then we add more to the second. The first one can only hold 2, so we put 2 in there. And then we only need 1 more, so we add 1 more in the outer shell. And we are done. And remember, when we add electrons, we have to pair them up after half filling the shell. But we don't need to do that yet, because there is only 1 in that outer shell. So that's it for the Bohr diagram of lithium. It's done. So now I want to show you a few tricks that you can use with the periodic table to help you create Bohr diagrams. So first off, the period the element is in will correspond to the number of orbits the Bohr diagram will have. So if your element that you're creating is in the first period, right here, it will have 1 orbit. If it is in the second period, if it's anywhere in this highlighted yellow area, it will have 2 orbits, or 2 shells. If it's in the third period, it will have 3 orbits. And if it is in the fourth shell, and I only highlighted the first 2 because we're only doing Bohr diagrams for the first 20 elements. But if it's in this fourth period, it will have 4 orbits. So that's just a quick little way to figure out how many orbits it's going to have. You can draw them in. Another fun fact is that if you count the number of elements in each period, it will match how many electrons are in that shell. So the first period has 2 elements in it, so there's only 2 electrons that will fill up that shell. For the second one, there's 8. So to fill up that shell, you use 8 electrons. The third one, there's also 8. So the third shell there has 8 electrons in it. And then the fourth one, I mentioned before, we're only doing the first 2 elements, so you'd only ever have to put in 2 electrons in that fourth shell. So we'll give a demonstration of how this works. We're going to choose an element, and then we'll figure out what the Bohr diagram would look like for that element. But unlike before, we're not going to use any information. We're just going to use its location on the periodic table to create a Bohr diagram. So here we go. We're going to pick this element. I'm not even going to say what this element is. Doesn't matter. So let's figure out how to draw this element. It is in the third period, right? It's 3 rows down. So we already know it has 3 shells, or 3 orbits. Now in the first shell, it's going to have 2 electrons. So we'll put those in, 2 electrons. In the second shell, it has 8 electrons. So we draw in 8 electrons. And then in the third shell, it has 1, 2, 3, 4, 5. And then we stop there because that's the element we're at. So we draw in 5 electrons. And if we count up all the electrons here, we'll see that there is 15 of them. So we know that it must have 15 protons as well. Now without the periodic table and the atomic mass, we can't really say how many neutrons are in here, but we got fairly far with this Bohr diagram by just looking at a location on the periodic table. So I just wanted to show you how helpful it can be to have a periodic table around when you're creating Bohr diagrams. So let's do a Bohr diagram of oxygen. Oxygen has an atomic number of 8, so it has 8 protons and 8 electrons. And it has an atomic mass of 16, so it has 16 minus 8, which is 8 neutrons. So here's our nucleus, 8p, 8n. If we look at our periodic table, there's oxygen. It's in the second row, which means, well, the second period rather. So it has 2 orbits, or 2 shells. The first shell is going to have 2 electrons in it, and we need to add up to 8, so we need 6 more. And we add those extra 6 in the next orbit, and we are done. There's a Bohr diagram of oxygen. Now valence shells and valence electrons are very important in chemistry. The outermost shell or orbit of an atom is called the valence shell, and the electrons in it are called valence electrons. So this right here is the valence shell, the outer shell or the outer orbit. I've been calling them orbits. That's the valence shell, and any electrons in that shell are valence electrons. And they're important because these are the ones that react with other atoms. So when there's a chemical reaction of some sort, the reason that chemical reaction is happening is because the valence shells of an atom are interacting. Now let's take a look at the patterns of the valence electrons in the periodic table. So if we look at the Bohr diagrams of a period on the periodic table, we can see that the number of valence electrons increases by 1 each step to the right. So in the first row, or the first period, we have 1 and then 2 valence electrons. In the second period, we have 1 and then 2 and then 3, 4, 5, 6, 7, 8 electrons in the valence shell. And then in the next period, we have 1, 2, 3, 4, 5, 6, 7, 8 electrons in the valence shell. And then in the fourth period, we only have 1 and then 2, and then we stop there because we stop at 20. So we can also see from looking at these Bohr diagrams that the number of valence electrons is the same for every element in a group or column. So for the first column there, the first group, those are the alkali metals, there is 1 valence electron. For the second group, the alkaline earth metals, there is 2 valence electrons, and that's the same for that whole group. And the pattern keeps going from there. It goes 3, 4, 5, 6, 7, and then a full valence shell. We say it's 8, but that top one there only has 2. But that's a full valence shell for the last column there. Now it's important because the number of valence electrons determines the way the elements combine to create compounds. And remember that each one of the columns in the periodic table all have elements that behave very similarly chemically. And those two things are linked. So the reason why they behave similarly in a chemical reaction is because they have the same number of valence electrons. Now if we take a look at the noble gases on the far right of the table, each of these noble gases has the maximum number of electrons in their valence shell. And this is what makes them very unreactive. So if you take a look, they can't fit any more electrons into their outer shell, and this is why they don't react with anything. The whole reason elements react with each other is so that they can fill up their valence shell. These guys already have full valence shells, so they have no interest in interacting with any other elements at all. So that's why they're unreactive. Alright, so that's it for this video. Tune in for the next video on isotopes and ions.